In the second part of the class, we will learn about the synthesis techniques for manufacturing or for producing nanomaterials. So we will learn the following technique, that is the chemical precipitation method, mechanochemical method, microemulsion method, reduction technique, chemical vapor deposition and sol gel method. So first of all, there are generally two approaches for synthesizing nanomaterials. First is the top-down approach, that is size reduction from bulk materials. The size of the bulk materials is reduced to nano dimension. And the second approach is the bottom-up approach, that is the nanomaterials is synthesized from atomic level. So in the following picture shows the two approaches, that is the top-down approach and the bottom-up approaches. First is the top-down approach. So here you can see a bulk material, a cube of any material, any chemical, and it is being reduced to smaller particles through various techniques. So this is the top-down approach. From the bulk, nanomaterials or nanoparticles are created. And the second approach is the bottom-up approach, that is through physical or chemical processes. So in this bottom-up approach, we are synthesizing this nanomaterial from the atomic or molecular level through various processes. We are synthesizing the nanoparticles from atoms through cluster formation, precipitation and all. So these two approaches are there for synthesizing nanomaterials. Generally, there are a wide range of techniques that can be categorized as top-down approach or as bottom-up approach. For example, ball milling and grinding. This is a top-down approach where through mechanical attrition process nanocrystalline substances are synthesized. Then lithography is another top-down approach where we use either optical lithography or an ion beam or an electron beam for doing this lithography patterns. Then generally in bottom-up approaches we have this solution-based synthesis, that is in your text, that is chemical co-precipitation method. Then vapor phase synthesis is there. When vapor phase itself, there are physical vapor deposition PVD technique as well as chemical vapor deposition CVD techniques, and then sol gel techniques are there, then laser ablation. So all these are examples for bottom-up approaches. So let us discuss more about this. So in a top-down routes are included in the typical solid state processing of the materials, and this route is based with the bulk material and makes it smaller, thus breaking up larger particles by the use of physical processes like crushing, milling or grinding. So in the top-down approach, we are by using these various physical processes like crushing, milling or grinding, we are reducing the size of this bulk materials. We are making it smaller and smaller. So usually this route is not suitable for preparing uniformly shaped materials, and it is very difficult to realize very small particles even with high energy consumption. So these are the drawbacks of this top-down approach. First is that it is not suitable for preparing uniformly shaped particles. That is, if some fraction of the nanoparticles are around 1 to 10 nanometer, some will be around 10 to 20 and some will be around 30 to 40 nanometer. So even the nanoparticles formed through these methods are not uniformly sized and uniformly shaped. Some might be cubical or some might be of some hexagonal shape or some other spherical shape. So all these are the problem of this route. Then it is very difficult to realize very small particles even with high energy consumption. So the main drawback is that this technique require high amount of energy. Even with the consumption of this high energy, it is difficult for us to obtain very small particles. So these are the drawbacks of top-down approaches like milling, grinding, crushing and all. Then and the biggest problem with top-down approach is the imperfection of the surface structure. Then such imperfection would have a significant impact on physical properties and surface chemistry of nanostructures and nanomaterials. So this is the main drawback. So these techniques will create nanoparticles with imperfections. So as a result of these imperfections, the desired properties which we want will not be obtained. For example, there might be some defect with the surface chemistry. If we are planning to use these nanoparticles for adsorption, gas adsorption purpose, so it might not be suitable. The adsorption capability will not be that much. So all these are the drawbacks of this top-down approach. So it is well known that the conventional top-down techniques can cause significant crystallographic damage to the processed patterns. Then coming to the bottom-up approach. The bottom-up approach refers to the build-up of a material from the bottom, atom by atom or molecule by molecule or cluster by cluster. And this route is more often used for preparing most of the nanoscale materials with the ability to generate a uniform size, shape and distribution. So these are the advantages of this bottom-up approach. Since we are preparing these nanoparticles by atom, by molecule, the result is that we are able to generate uniform sized or uniform shaped or uniformly distributed particles, nanoparticles, and it effectively covers chemical synthesis and precisely controlled the reaction to inhibit further particle growth. So here we are able to precisely control the growth of the nanoparticle so that the nanoparticle will not precipitate out and will not go out of this nano dimension. Although the bottom-up approach is nothing new, it plays an important role in the fabrication and processing of nanostructures and nanomaterials. Synthesis of nanoparticles to have a better control over particles' size, distribution, morphology, purity, quantity and quality by employing environment-friendly economical processes has always been a challenge for the researchers. So the researchers, the main challenge they face, the researchers who work in the field of nanochemistry or nanotechnology, for them they have to prepare nanoparticles that have better morphological control or nanoparticles having high purity or that are defect free, and they have to prepare that in greater quantities. So sometimes for the industrial purpose we have to scale up this synthesis technique. So all these are the challenges faced by the researchers, and also most of the techniques they might not be environment friendly. If you are using certain solvents, organic solvents for this precipitation and all, they might not be environment friendly. Therefore using aqueous medium is more benign in nature. So all these are the challenges faced by the researchers. Now we will learn about the first technique which is given in your text, that is the mechanochemical method. So in a mechanochemical method, as the name indicates, it involves a mechanical action, isn't it? So in a mechanochemical reaction, these are defined by the reactions induced through mechanical energy for the synthesis of nanoparticles. And commonly these reactions occur between solids with no or minimal addition of solvents. So the first point is that in a mechanochemical method, it requires mechanical energies. Mechanical action or mechanical energy is involved for the synthesis of this nanoparticles, mainly for the synthesis of inorganic nanoparticles. And the second point is that these reactions are occurring between the solids. So therefore there is either no use of solvents or very small or minimum use of solvents for these type of synthetic methods, because the reactions are occurring in the solid state itself. And typical reaction setup occurs in ball mills such as shaker or planetary mills with balls of various sizes placed in together with the reactants. So inside a ball mill or a planetary mill, balls of various sizes are placed along with the solid reactants which we want to react. And this type of chemistry not only severely eliminates solvent wastage, it also allows for quantitative and fast reactions to occur between the solids. So this type of method it eliminates solvent wastage, because we are either using no solvent or we are using very minimum amount of solvent for this technique. And also it allows for the quantitative and fast reactions to occur between the solids. So here in this video you can see a ball milling technique. Here you can see that there are so many heavy balls placed inside this mill, and along with that our reactants are also mixed. So as we increased this speed of this milling, what happens is that the particles will collide with each other and with the among the balls, and as a result the particles, the solid state particles will react, and minute or nano particles are formed. We can see this video for some time. So here you can see this ball mill revolving, and as the speed increases, the grinding action is also occurring, and at this subcritical speed you can see the particles, and they are being grinded together with these balls. And again, when the speed is increased, this grinding actions efficiency will also increase. Now at the supercritical speed, you can see how fast these balls are colliding with the reactants and how this grinding is occurring. So this is the ball milling technique. So now coming back to the text, in the milling synthesis, reactants are only exposed to one another at the colliding surface, and the contact point of the reactants allows for product to be formed which breaks off the original reactant particles. And this technique has been shown to have advantages over other methods of producing nanoparticles in terms of low cost, small particle sizes, low agglomeration, narrow size distribution, and uniformity of crystal structure and morphology. So these are the advantages. So these techniques have the following advantages over the other technique. First is the low cost. The cost is very low. Then small particle sizes. So we are able to obtain nanoparticles when smaller than 50 nanometers through this ball milling technique. Then low agglomeration, that is the nanoparticles formed will not agglomerate together and will not join together and form larger particles. And then narrow size distribution. So narrow size distribution means the particle sizes will be in a range of for example 10 to 50 nanometer, but it will not be within the range of 10 to 500 nanometer. So the distribution of size range will be narrow. And uniformity of crystal structure and morphology. Then carbonated hydroxyl apatite nanofibers were prepared via our action among CaHPO4, 2H2O, CaCO3 and urea in aqueous solution. So here this is an example given. So we are taking these solid reagents like calcium hydrogen phosphate and calcium carbonate and urea in aqueous solution, and through this mechanochemical method we are grinding these reagents and we could prepare this carbonated hydroxyl apatite nanofibers. This is an example for the mechanochemical method. So many other examples are also available in the literature. And the second technique is the chemical precipitation technique. So in a chemical precipitation method, the constituents are weighed in stoichiometric proportion and dissolved to get a Stokes solution. All the cations are then co-precipitated to achieve a complex formation by selecting suitable precipitating agent and pH. So in this case, in this technique, what we do is that if we want to prepare an iron oxide nanoparticle, so it can be prepared from ferric chloride and ferrous chloride. So we weigh this stoichiometric amount of ferric chloride and ferrous chloride, that is we prepare an aqueous Stokes solution of this, for example a 2 millimole or a 3 millimole of this Stokes solution, and using a suitable precipitating agent, for example a precipitating agent like sodium hydroxide or potassium hydroxide can be used to convert this ferrous chloride or ferric chloride to its hydroxide form. So and we are adjusting or controlling the pH also for this precipitation. So we are precipitating it at a specific pH. In this case at a basic pH we are doing the precipitation. So in case of oxides, the precipitate could be in the form chemical form of hydroxide, carbonate, oxalate, etc. So that after decomposition it is converted into oxide. So the precipitate we are obtaining like hydroxide, or we can obtain a carbonate or an oxalate precipitate. So what we do is that we just decompose it, that is we heat it, or through some other technique we convert it into the oxide form. Okay, so if we are preparing this ferric or ferrous oxide, if we are using this ferric chloride by using a precipitating agent like sodium hydroxide, we are able to convert it to the hydroxide form, and then again through thermal decomposition we are able to obtain the iron oxide form. Okay, so this is how we do this method. So in this process, the particle size is determined by the solution concentration, rate of precipitation and calcination temperature. So by adjusting the concentration of the stock solution, for example, if we want a smaller sized particles, we can take lesser amount of lesser concentration of the stock solution. Similarly, we can also change the rate of precipitation. Rate of precipitation means if you are adding this precipitating agent very fast, the precipitation will be carried out in a much faster rate. But if you are adding it in a drop-wise manner with constant stirring, magnetic stirring and all, the precipitating rate will be very slower. Then smaller sized particles can be obtained. Then again, the calcination temperature is also important. For different type of nanomaterials, the calcination temperature is very significant because it can cause phase changes in the nanomaterials. And then however, during the drying of the precipitate, there is a possibility of agglomeration of the particles, and hard cake obtained in this step needs ball milling to get nano-sized materials. So here after drying, after calcination and drying and all, there is a possibility that these nanoparticles form. We know that it is having high surface energy. Nanoparticles will possess high surface energy because the number of atoms on the surface is greater than that in the bulk inside the material. So therefore, as a result, to lower its surface energy and to attain stability, what this nanoparticle do is that it will agglomerate with adjacent particles and then it will form larger sized particles. So the nano dimension is lost. So in such a case, what we do is that after this drying, we again will subject it to ball milling process so that it will we will get the reduced dimension of the powdered form of the material. So this is the technique of chemical precipitation or chemical co-precipitation. Then the third technique is the sol gel method. This is a very important technique. So, and it is widely used for producing glassy and ceramic nanomaterials with nano-size distribution and controlled chemical composition at comparatively low temperatures. So now you know the major advantage is that this sol gel technique, it requires only a low temperature when compared to all the other techniques. Okay, sol gel techniques is carried out at very low temperature, and it is used mainly for producing glassy and ceramic nanomaterials with narrow size distribution and controlled chemical composition. That is, we can control its chemical composition so that we can attain high purity. And this synthetic method generally allows control of the texture, the chemical and the morphological properties of the solid. The major advantages of the sol gel technique includes molecular scale mixing, high purity of the precursors and homogeneity of the sol gel products with a high purity of physical, morphological and chemical properties. So this is the major advantage. We are able to obtain nanomaterials of very high purity because the precursors we use are of very high purity. Okay, we purchase it from the suitable suppliers so that we can use the high purity precursors, and therefore the composition can be controlled, and also the homogeneity of the sol gel products with a high purity of physical, morphological and chemical purities can be attained. So in a typical sol gel process, a colloidal suspension or a sol is formed from the hydrolysis and polymerization reactions of the precursor. So here you can see a picture in your text, and this is a schematic representation of a typical sol gel method. So here in the first container, or in the first beaker, you take a metal alkoxide solution. Okay, so this is a precursor used. From this metal alkoxide solution, you are going to prepare this metal oxide nanoparticle, the nano powder form. For that, the first step is the hydrolysis and polycondensation. You have to do hydrolysis reaction, and then you have to undergo this polycondensation process. Condensation means the loss of smaller molecules like water molecules. So here, after these two steps, you will get a sol, okay, a sol form in the second beaker. So here, the sol form, after obtaining the sol form, you have to use a dehydrating agent so that you can remove the water molecules. Okay, and in this step you will get the gel form. Then this gel form, after this process like aging, washing and drying, you will get nano powder. So this is a representation of a typical sol gel process. So here the colloidal suspension or a sol is formed in between. So that is why it is called a sol gel process. Here the synthetic method involves the formation of a sol as well as a gel. And from the hydrolysis and polymerization reaction of the precursors, which is usually inorganic metal salts or metal organic compounds such as a metal alkoxide. Gelation is achieved by means of chemical dehydrating agent with surfactant. So here for the gelation we use any chemical dehydrating agent. Okay, dehydrating agent means a chemical that can remove water molecules, water of hydration. So dehydrating agent along with the surfactant is used. Why we use a surfactant? It is to prevent the agglomeration of these smaller particles. If these particles agglomerate, then the particle size will go beyond the nano range. Therefore, we are using a dehydrating agent along with a surfactant. Then, for example, 2-ethyl hexanol and a surfactant are commonly used. Okay, not only 2-ethyl hexanol, so many dehydrating agents and surfactants are used nowadays for the sol gel techniques. Okay, you can simply go through the internet and just type the sol gel method and go for images. You can get so many information about this technique. Okay, and now it is a widely used technique for synthesizing nanomaterials. And after gelation, the wet gel can be optionally aged in its mother liquor. Mother liquor means the medium in which the reaction has been carried out, and the medium having all these reactants, unreacted reactants, solvents, etc. This is the mother liquor. So after this gelation, we keep this thing inside the mother liquor for some time, or we transfer it to another solvent or in another solvent, and it is then washed. So this is the process of aging. So the time between the formation of a gel and its drying, known as aging, is also an important parameter. So the time we allot for this step, for aging process, is also an important parameter. So the sol gel parameters such as the type of precursor, type of solvent, water content, acid or base content, precursor concentration, and temperature affect the structure of the initial gel. So now we know that we have obtained a gel here. So for the structure of this gel, that is the microstructure of this gel, is affected by all these parameters. Which are the parameters? Parameters such as type of precursors, the initial reagent we are using, whether it is a metal salt or a metal alkoxide, metal organic compound. So the type of the precursor, then the solvent type, whether it is an organic solvent or an aqueous medium. So the solvent type will influence the reaction or the quality of the structure of the gel, then the water content, the pH of the medium, then the precursor concentration and the temperature. Okay, temperature will also affect the structure of the initial gel, and in turn the properties of the material at all subsequent processing steps. So the gel is then dried and calcined. Calcined means it is heated. Okay, it is heated in a hot air oven, and it is calcined to get a reacted product. One of the more important applications of sol gel process is to carry out zeolite synthesis. So it is widely used for synthesizing zeolite material. So this is all about the sol gel process. Now we come to micro emulsion method. So you might have heard about water in oil or oil in water emulsions. Okay, so here in a micro emulsion, it is generally defined as a system composed of a mixture of aqueous phase and oil phase, surfactants and co-surfactants. So these components are present in a micro emulsion. You have an aqueous phase, basically the water medium, then you have an oil phase, that is the non-polar medium, then you have a surfactant and co-surfactants. So as you know, surfactants and co-surfactants, they have a polar head and a non-polar tail. Okay, you might have learned the basic structure of surfactant molecules. So the concept of the microemulsion process involves thoroughly dispersing the water phase into the oil phase using a surfactant, followed by the addition of precipitating agent. Nano-sized microemulsion droplets are formed. So here in this step, we are thoroughly dispersing the aqueous phase into the oil phase along with the surfactant. Okay, along with the surfactant, we are thoroughly dispersing these two phases, and also we are adding the precipitating agent and the reactants. Okay, so all these are mixed together. The very first step of nanoparticle formation in microemulsion system is the chemical reaction between the reactants and precipitating agents. Here in the diagram you can see these two boxes here. So in the first box you can see emulsions. Okay, emulsions is micro droplets, and here you can see the surfactants. Inside the surfactants there is an inorganic salt A. This is one of the reactant. Okay, inorganic salt A, and this reactant is dispersed inside the water or aqueous medium. This is the first system. In another system or in another container, you are taking water, aqueous medium and the precipitating agent, that is the reactant B. So again these two are emulsions only. Okay, and in the next step what you do is that you mix these two containers, these two reactants, that is the reactant A and reactant B, that is a precipitating agent, will come in contact. So the collision between droplets allows the reactant interchange within these micro particles. Okay, So you can see that when the collision occurs, the surfactants will rearrange to form this small micro reactors, and inside these reactors collision of this reactants A and B will occur, and in the next step nucleation and growth occurs. Then finally you will get this nanoparticles inside these small micro reactors, that is inside these surfactants. So the nanoparticles will not grow out of the surfactant because the surfactant is efficiently covering or arresting the growth of the nanoparticle inside this space. Okay, so the product is obtained as nanoparticles. So the very first step of nanoparticle formation is in microemulsion system is the chemical reaction between the reactants and precipitating agents. Then each tiny droplet acts as independent microreactor for producing the desired compound and provides a confinement effect that prevents particle to particle contact. Okay. So here the basic chemistry is all similar, just like a co-precipitation or a sol gel or whatever it is. The basic chemistry is similar, but the techniques we use, the step by step techniques we adopt for the synthesis is different. Here for example, we are using an inorganic salt A. For example, let it be the one we formerly discussed, ferric chloride. Okay, and we are using a precipitating agent in the second content, for example sodium hydroxide. Okay, and when these two are mixed, we will get this sodium hydroxide form. Then these sodium hydroxide salts will grow, nucleate, and then we get ferrous hydroxide salts inside these. Okay, and if we are heating these or kept it for aging, we will gradually get this iron oxide nanoparticles. So as a result, particle nucleation, growth and coagulation can be significantly constrained. So inside these microreactors, the particle size remain in the nano range itself. So here there is a confinement effect. Okay, confinement means an arresting or a hindrance to move from beyond this limit. Okay, there is a confinement within this region. So the particles will be in the nano range itself. The chemical reactions take place rapidly in these micro cavities containing the desired reactant colloid, allowing the synthesis of nano-sized powders. The microemulsion technique promises to be one of the versatile precipitation method which enables to control the particle properties such as mechanisms of particle size control, geometry, morphology, homogeneity and surface area. So this is since a clumsy sentence. So nothing but this technique is a very versatile technique, and it is used a better technique used for with you offering better particle size control. We can get good geometry, or we can have a better control over the morphology, homogeneity as well as the surface area of this nanoparticles formed through microemulsion method. Then colloidal Fe3O4, then cadmium sulfide, zinc sulfide are some of the nanoparticles prepared by this method. Now you have chemical vapor deposition or CVD. So in this process, it is often used in the semiconductor industry to produce high purity, high performance thin films. So in a typical CVD process, the substrate is exposed to volatile precursors. So here you know that in this CVD technique we use a substrate, and over the substrate our material is coated. For that we use a volatile precursor. Okay, we use a volatile precursor which react and or decompose on the substrate surface to produce the desired film. So through this technique we are able to prepare two-dimensional nanomaterial. Okay, we are able to obtain a two-dimensional thin film or a two-dimensional coating, a nano coating over a particular substrate. So either the volatile precursor deposit over the substrate, or it will react with the substrate and form a thin film over it. Frequently volatile byproducts are that are produced are removed by gas flow through the reaction chamber. So during this reaction some byproducts are also formed. Okay, some volatile byproducts are formed, but these are removed through the chamber by this gas. So here you can see a carrier gas which is flowing through this chamber, and it is a gas exhaust here. So this is a gas inlet and this is a gas exhaust, and you have a reaction chamber, and inside this reaction chamber you can see the substrate and a nanofilm coated over the substrate. So all the unreacted volatile byproducts are eliminated through this gas exhaust by the carrier gas. The quality of the deposited material strongly depends on the reaction temperature, the reaction rate and the concentration of the precursors. So all these are the parameters which we adjust for synthesizing high quality, high purity two-dimensional nanomaterials. The advantages of this method include the uniform coating of the nanoparticles or nanofilm. So this is one of the major advantage of CVD technique, that is uniform coating of nanofilm can be attained. So this uniform coating means it will be defect free. Okay, and however this process has limitations, including the high temperatures required, and it is difficult to scale up. So this technique, since it is a chemical vapor deposition method and we have to convert the reactants to volatile precursors, it requires a very high temperature. So this is one of the disadvantage of this technique, whereas in sol gel technique and all, low temperature would be enough. But here in this case in CVD, high temperature is required. Because of that, high energy consumption is there. Therefore it is difficult to scale up. So if we want to prepare this thin film material in large quantities in industry, it is very difficult to scale up using this type of method, because it is not economically viable. And then CVD has also been utilized for synthesis of a technologically important material, that is carbon nanotube. And besides this SN4 plus doped TiO2 nanoparticle, that is tin doped titanium dioxide nanoparticle films were prepared by CVD method, and found that more surface defects were present on the surface due to doping with tin. Now the last technique is the chemical reduction. So reduction, as the name implies, it is either the addition of electrons to it, or it is either the addition of hydrogen atoms. So chemical reduction is the most frequently applied method for the preparation of metal nanoparticles as stable colloidal dispersions in water or organic solvents. So using the chemical reduction method, we are able to prepare metal nanoparticles, and we obtain it in the form of colloidal dispersions either in aqueous medium or in organic solvents. And commonly used reducing agents are boron hydrate, citrate and elemental hydrogen. So these are the common reducing agents used in chemical reduction technique. Then the reduction of metal ions in aqueous solution generally yields colloidal metal particles with diameters of several nanometers. Initially, the reduction of various complexes with metal ions leads to the formation of metal atoms, which is followed by agglomeration into oligomeric clusters. So, the first step, what we do is that the metal precursor solution, we reacted with these reducing agents. As a result, the reduction of the metal ions in aqueous solution will give colloidal metal particles with diameters of several nanometers. So as a result of this initial reduction process, the reduction of various complexes with metal ions will lead to the formation of metal atoms. So initially we are getting this metal atoms, but metal in atomic form is not stable. So it will agglomerate and form small oligomeric clusters. That is, clusters means a group of only few atoms. So these clusters eventually lead to the formation of colloidal metal particles. So these clusters are also having very high energy. So these oligomeric clusters, the name given for clusters with a few 1 to 50 number of atoms. So these clusters, because of its high surface energy, it will agglomerate and eventually it will give colloidal metal particles. So group 6b metal hydrates like chromium chloride, molybdenum chloride, tungsten chloride, all these can be reduced into their corresponding metals by using hydrates like sodium triethoxy boron hydrate. Okay, NaBeT thrice H. This is sodium triethoxy boron hydrate. So this is a reducing agent and it will supply hydrogen, elemental hydrogen, and this reaction is carried out with toluene as a solvent at room temperature. So we have to use a solvent which is toluene. So toluene and tol is not a this type of synthesis, basically it might not be so environmental friendly because we are using organic solvents like this. So this is one of the drawback of this chemical reduction technique. So for chemical reduction technique, we are using a reducing agent like a boron hydrate, citrate or an elemental hydrogen. And first this metal precursors are reduced to metallic atom, metal atoms, and metal atoms will agglomerate to give oligomeric clusters, and these oligomeric clusters will eventually give colloidal nanoparticles. So this is the chemical reduction technique.